Let's summarize what we just did and try some examples. All right, so on the next 4 slides, we're just going to put together a summary of our various different geometries. Now, you'll notice that there's a column here I have for hybrid. This is for our hybrid orbitals. We're about to cover that next. So I'm going to write some stuff in on the hybrid orbitals. I understand it's not going to make any sense to you yet. That's okay, because I'm going to go over all of this coming up. But I wanted to make sure that we summarized the different things with our various geometries before we jumped into our orbital hybridization. Okay. So on this slide, we're going to take a look at a summary of our linear and our trigonal planar geometries. So where we have 2 and 3 electron groups. All right, so for my first one, number of electron groups, I have 2 bonding and 0 lone pairs. So I have a total of 2 electron groups. So my orbital geometry here is linear. Everything bonding, so my molecular geometry is also linear. My bond angle is 180 degrees. All right, common example of this, carbon dioxide. Okay, and our 3D sketch in 3 dimensions, it's just a straight line. So our 3D sketches are not going to be proper Lewis structures. All right, they're just going to be a brief representation of in 3-dimensional space, how is everything oriented around each other. All right, and then again, I'm going to fill in this hybrid category column for you, but we'll explain it all in the next video. Okay, this is going to have an SP hybridization. Okay, all right, now I have my AX3 classification. 3 bonding, 0 lone pairs, total of 3 electron groups. Okay, so this is trigonal planar. When everything's bonding, same thing. Okay, and this is where we had our 120-degree bond angles. All right, and then we'll do our boron trifluoride. Okay, all right, and in 3-dimensional space, it's just a flat triangle. Okay, and here the hybridization is sp2. All right, and then last on this page, I have 2 bonding and 1 lone pair with our AX2E classification for a total of 3 electron groups. And so our orbital geometry is trigonal planar. And our molecular geometry now is bent. Okay. All right, and this is where we get our less than 120-degree bond angles. Okay, ozone is a common example of this one. I'm only going to draw one of the resonance structures because remember, when we have resonance, all the resonance structures have the same geometry, so I'm just going to draw one of them. Okay, it's neutral because we have a minus here and a plus there. Okay, and our 3D structure, or our 3D sketch rather, is like that. Okay, so again, the 3D sketch, this is not a Lewis structure. All right, so we can be missing double bonds, we can be missing, lone pairs around our surrounding atoms, those sorts of things. All that 3D sketch is just in 3-dimensional space, how does everything fit relative to each other? And these are the, last of the ones where it's going to be super easy where we don't have to use wedges and dashes. Okay. All right, and this is also, as we will learn in a little bit, under an sp2 hybridization. Okay. All right, now let's turn to our classifications where we're going to end up with 4 electron groups. Okay, so our first one, we have 4 bonding, 0 lone pairs, so we have a total of 4 electron groups. All right, this is our tetrahedral. Okay, everything's bonding, so our molecular geometry is also tetrahedral. All right, and this is our 109.5 degree bond angle. And the most common example of this is methane. Okay. All right, so we draw it all flat, but remember, tetrahedral, it's poking out in places. It's not super flat. So here is where we show what's in the plane, what's coming out of the plane, and what's going back behind the plane. So there's our 3-dimensional sketch. And as we will learn, this is an sp3 hybridization. Again, that's coming up. Okay. Our next one, I have 3 bonding and 1 lone pair. 3 plus 1 still gives me a total of 4 electron groups. So our orbital geometry is tetrahedral. Okay, and this is our molecular geometry where we are trigonal pyramidal. Okay. Now remember, those lone pairs squish that bond angle in, so that's where we get our less than 109.5 degrees. Okay, I have 2 dots there for some reason. That's better. All right, we'll do ammonia. Okay, all right, and then we'll sketch it in 3 dimensions. I'll put the lone pair in the plane, this hydrogen in the plane, this one coming out, and that one going back behind. Okay, and we're still sp3. All right, and then our last classification here, 2 bonding, 2 lone pairs for a total of 4 electron groups still. So our orbital geometry is still tetrahedral. Okay, this is where our molecular geometry is bent. We're still less than 109.5 degrees, and we'll do water as our example here. Okay, and then our little 3D sketch, I'll put that lone pair in the plane, that lone pair in the plane, hydrogen coming out, and back behind. And this is still also sp3. Okay, so far so good. Okay, all right, now we'll move into our crazy trigonal bipyramidal. All right, so I have 5 plus 0, so I have 5 total electron groups. So this is where we are trigonal bipyramidal. Okay, when everything's bonding, the molecular geometry is the same. All right, now this is the one where we have 2 different bond angles. All right, so our axial to equatorial, that was the 90 degrees, and then our equatorial, that was the 120 degrees. Okay, all right, we'll do our phosphorus pentachloride here. All right, and now our 3D sketch. So in the plane, in the plane, in the plane, and coming out and back behind. Okay, and again, 3D sketch. We're just showing everything relative to where it is in 3 dimensions using those wedges and dashes and stuff. So we don't need all the lone pairs on the surrounding atoms. All right, and as we'll learn, this is what we call an sp3d hybridization. Okay. All right, next up, I'm going to take 4 plus 1, 4 bonding, 1 lone pair. I'm still going to get 5, so my orbital is still trigonal by pyramidal. Okay, now this is the one where it looks like a teeter-totter or a seesaw, which is why we call it seesaw. Okay. All right, and here's where we remove or replace a bonding atom with a lone pair on that equatorial region. Okay, so our axial to equatorial becomes less than 90 degrees. And it doesn't really affect the equatorial as well, or as much. So I'm going to keep that at 120. Okay. All right. There's the Lewis structure of our example. Okay. And so remember, we don't take it off the axial regions. That lone pair is on equatorial region. Okay, and so if you tip it on the side, that's where you get that teeter-totter seesaw look. All right. We keep that sp3d. Okay, our next one, I have 3 bonding and 2 lone pairs. 3 plus 2 is still 5. So we're still a trigonal bipyramidal. Okay. All right, we're going to remove another one off that equatorial region, and so it ends up being T-shaped. Okay. Now, we don't have anything else left equatorially except for 1 atom. So equatorially, we don't consider bond angles anymore. Now we're just considering with, the axial to the one that's left on the equator, the axial to the one that's left on the equator, what our bond angle is. So we're only looking at that axial to the equatorial bond angle, and that is still less than 90 degrees. Okay. All right. There's an example there, chlorine trifluoride. Okay, and then we'll draw our 3D sketch. All right, and so that's where if you turn it on the end, it looks like a T. And then we've got a lone pair here and a lone pair there. Okay, and we're still sp3d here for this hybridization. All right, we have one more to consider here. I'm going to do 2 plus 3 is still, coincidentally enough, 5. So our orbital geometry is still trigonal bipyramidal. Okay, at this point, we've taken everything off that equatorial region, and so our molecular geometry is linear. So our bond angle is 180 degrees. All right, here's our example. All right, and then our formal charge goes there on that center iodine. Okay, and so there's our 3D sketch, and we're still sp3d. Okay, all right, we have one more summary page, and that is our 6 electron group summary. Okay, so 6 plus 0 gives us 6. So this is our orbital geometry that is octahedral. Everything's bonding, so our molecular geometry is also octahedral. Okay, our bond angles here are 90 degrees. Okay, and we'll do sulfur hexafluoride as an example. Okay, all right, now with our 3D sketch. Remember, it looks like we kind of have a square going around the center. So this is the one where we're going to show this, okay? And then we're going to finish that square on either side. Okay? Our hybridization here is going to be sp3d2. Okay? All right, almost done with our summary here. And then we're going to do some practice problems. All right, we've got 5 plus 1, which equals 6. So we're octahedral. For our orbital geometry, our molecular geometry, this one is the square pyramidal. Okay. We're going to keep to those 90-degree bond angles. All right, we've got some bromine pentafluoride here. Okay. Okay, and now for our 3D sketch. We have that there, and then we still have that square. Okay, and we're still sp3d2 on that hybridization. All right, last one for our summary. 4 bonding, 2 lone pairs, so 4 plus 2 gives us a total of 6 electron groups. So our orbital geometry is still octahedral. All right, and this is where now we are square planar. Okay, our bond angles are still 90 degrees. Okay, xenon tetrafluoride. So there's our Lewis structure. And now for our 3D sketch. Okay, and this is still SP3D2. All right, so that's a summary there of all the different geometry types with the hybridization included for you to use as a, overview study tool. Now, let's try some examples. So I have 5 examples here. The goal is to draw the Lewis structures, predict the geometries, and the bond angles. All right, so let's give these a shot. So I'm going to go through these 5 with you, and then I have several more examples that are for you to try on your own without me walking you through them or telling you what the geometry is, because I don't want to give. So that's the double-edged sword on these. Sometimes I'll give, if it's a numerical problem, I'll give the final answer. But for something like this, where it's the geometry, and your job is to be able to not just assess the geometry, but to draw the Lewis structure. If I tell you the geometry, then you can backfill the Lewis structure without having to think through it. All right, so the other example problems, I'm not going to tell you. If you are one of my students and I am your instructor, you can always email me and ask me for those. But let's try these. Okay, so A. Okay. So if you count up the electrons, you have 40 total electrons that we have to take into account. And we end up with a structure that looks like this. Okay. All right, so when I look at this, I have my central atom, and I have 5 surrounding atoms and no lone pairs. So I have 5 total electron groups. So my orbital geometry is that trigonal bipyramidal. Okay, and my molecular is also trigonal bipyramidal because everything's bonding. Okay, and so our bond angles, our axial to equatorial bond angle is our 90 degrees, and then the equatorial is the 120 degrees. Okay, all right. B, we had this right here, okay? This one's going to have a total of 22 electrons that we need to account for. So remember, as you're doing these, if you're not confident that you're getting everything, count those electrons and do a ledger and subtract as you go to make sure that you are indeed using all of the available electrons. Because the valid Lewis structure uses exactly the number of valence electrons you have available to you. No more, no less. If you come out unequal on your electrons, if you don't hit 0 at the very end, your structure is incorrect. All right, make sure you're using all your valence electrons. Okay. So this one looks like this. It has a formal charge of -1 on that central iodine. Okay. So I have my central atom. I have 2 bonding, and I have 3 lone pairs. So 2 plus 3 is a total of how many electron groups? 5. So our orbital is our trigonal bipyramidal again. And our molecular is linear. Okay, we're linear, We only have that one bond angle left, and that's the 180 degrees. Okay? All right, next up, we have a lovely compound with xenon. Total of 42 electrons that are necessary. And we get a structure that looks a little something like this. Okay. All right, on this structure, we end up with a formal charge of +1 on the xenon and -1 on the oxygen, so it's still neutral there. +1 and -1 cancel out. Okay, so we've got our central atom. I have 5 surrounding atoms and 1 lone pair. So what's 5 plus 1? 6. Okay, so that means our orbital geometry is octahedral. And our molecular is square pyramidal. Okay, and our bond angles here are 90 degrees. All right, I need some more space to write. All right, 2 more, and then you're on your own. Okay, so here you should be keeping track of 36 electrons. Okay, and the formal charge goes on this iodine here. Okay. All right, so I have my central atom. I have 4 surrounding and 2 lone pairs. So what is 4 plus 2? 6. So our orbital geometry is octahedral again. Okay, and our molecular is square planar. And our bond angle is 90 degrees. Okay. All right, last one. Okay, and there's 32 electrons to track here. All right, so I'm going to draw the structure that has the least formal charges. That's the better structure. Yes, you can draw this with all single bonds to the oxygens. You can get a valid structure off of that. However, what that ends up doing is that it ends up tossing a formal charge on every single one of the oxygens and the chlorine. Try it. Try drawing it and assigning all the formal charges. This structure only has formal charge on a single oxygen. So this is the better structure. Okay, so we only get a formal charge there. Okay. All right, so I have a central atom and I have 4 things bonded to it. That's it. So we have 4 total electron groups. So what's this one? Tetrahedral. So our orbital geometry is tetrahedral. And our molecular, because everything's bonding, is also tetrahedral. Okay, and our bond angle is 109.5 degrees. Okay, so it's not enough for you to simply copy what I do. You have to work these problems yourself. So here's a whole bunch more to try on your own. Once again, if you are in one of my classes, try these. You can email me. I'll send you the answers. but only if you send me what you did. I'm not just going to send you the answers so you can backtrack. I need you to, if you want the answers from me, you need to send me all of these complete with what you did, and then I'll send you back the answers. Okay? All right, give these a shot. Next up, hybridization.